Okay, welcome back. So the next talk will be by Paolo Braccia from Los Alamos, who will be telling us about quantum convolutional neural networks.
Cool. Okay. So thank you for the introduction, and thank you for getting my last name right. Like, very few people do that. And thank all of you for being here. So before I tell you how quantum convolutional neural networks can be effectively classically simulated, let me shout out to my amazing friends and co-authors, Pablo, Manuel, Zoe, Lukasz, and Marco, and particularly to Pablo, that was our student at that time and who did all the very heavy numerics needed to carry out this project. So let me start by giving you a bit of context. Although I imagine that most of you might have already heard of quantum machine learning, let me just recall that this is the field that tries to combine quantum computation and machine learning in order to, so to speak, achieve the ultimate limits of data processing as allowed by nature. And over the past few years, a lot of very good people put a lot of effort into designing and finding learning models that could achieve a speed up, an advantage, or even maybe a supremacy against their classical counterparts at solving classical machine learning problems. But at least in my opinion, more interestingly, at finding quantum machine learning models that could solve inherently quantum problems in a data-driven fashion. And among the latter are quantum convolutional neural networks that were introduced in this paper here, which then became a Nature Physics. And this model has become kind of the most celebrated / hyped and glorified model among the quantum machine learning ones in the literature, mostly because of a few remarkable perks that it has. First of all, it's shown a great deal of heuristic success at classifying all the quantum states data sets that have been thrown at. Then there's the fact that it being shallow, as we'll see in a moment, makes it suitable for near-term quantum devices, which are, as probably you know, small and noisy. But probably more importantly, what makes them stand out from the rest of the models is that they are provably free of barren plateaus. Barren plateaus being one of the greatest limitations to the trainability and hence success of quantum machine learning models, because basically this is a phenomenon that makes so that upon random initialization, your learning model has no gradient, so you don't know how to train it, basically. So QCNNs are free of this problem. But this might not be the greatest of news, and indeed, this last observation is kind of the motivation of all this work, because in this other work, we put forward this connection between the trainability of a quantum machine learning model and the possibility of classically simulating it, so in a way dequantizing it. And our claim there is that are the very features, if you want, that lead to the proof of absence of barren plateaus that can be turned against the model itself to construct the classical simulation algorithm. Now, this is a statement on average, meaning that on average you would sample points from the training landscape and you would be able to simulate in a vicinity of them. In this work, we wanted to go farther and show that you might be able even to simulate a full successful training by staying in the classically simulable space. And indeed, what we argue here, and what I will try to convince you, is that the action of unitary QCNNs is simulable in a stronger sense of enabling a completely classical training. So you will never actually need to deploy your QCNN quantumly. All right. So the way we can show this is by asking ourselves and answering a couple questions. So first of all, we want to address how QCNN processes the information it's fed with, so like what kind of properties of the input states it's actually looking at. And secondly, we want to understand, among all the data sets that have been used in the literature to test QCNNs and to, again, like kind of glorify them, where are the classifying properties encoded in these states? And once we have information from these 2 points, we can naturally see where and how to construct a classical algorithm that can simulate QCNNs. Now, for all of you that are still wondering what the heck is a QCNN, it's just a parameterized quantum circuit model, which is, I'll refer to that screen there, which is basically composed of these repeated blocks each block being made of 2 layers, a convolutional and a pooling one. And you can think of the convolutional maps, both of them could be parameterized, of course. So the convolutional maps C of theta as rotating the information in the input Hilbert space, whereas the pooling maps do sort of a coarse graining of the information, dropping part of it and reducing the size of the Hilbert space. The idea being that you hope for only the relevant feature to flow through the architecture and survive till the last order 1 qubits where you actually take the measurements. And here we will focus on a restriction of this to unitary QCNNs, where the convolutional maps are correspond to conjugation by a unitary, and particularly they are this kind of brick-layered 2-qubit architecture, whereas the pooling maps are non-parameterized and they just basically trace out half of the qubits at each layer. So I'll use only phi of theta as a symbol for the QCNN from now on. Then, of course, how do you actually use a QCNN? Like, what kind of problems are we going to tackle? Basically, it's going to be quantum dataset classification. So this will fall under the umbrella of supervised quantum machine learning tasks. The idea being that we'll be given some data space R consisting of some distribution of quantum states. And associated with that, there will be an integer valued label space gamma, where basically each of these integers just tells you the class a quantum state can belong to. Think of it in a classification of phases of matter, like quantum states would be ground states of some Hamiltonian model, and the integers just the phases they belong to. And the idea is that you will parameterize some function, h of theta, to approximate the true relation between states and labels, f. And then you would try and fit h of theta to f as best as possible by repeatedly querying some training data set consisting of states and their true labels, so ρi and yi. In the QML setting, one defines h of theta by defining the expected or predicted labels as the expectation values at the end of their favorite parameterized quantum circuit, in our case, the QCNN. So you would feed the input state to the QCNN, measure something, and declare that your label. And once you have the predicted label y bar, you can construct your favorite loss function, the loss function being fundamentally the measure of error you're making in using the predicted labels as opposed to the true labels yi. And then you can solve this training task by minimizing the error you're making on the training set. And then you would define the trained model or optimal model as the model evaluated at the optimal parameters. Now, a core assumption of quantum machine learning is that you need a quantum computer to do that. I mean, it's quantum machine learning. So you expect the prediction of the phases or the labels to be hard and to have to be carried out on a quantum device. If the model is classically simulable, though, there's no need to do that. So what we mean by classically simulable, of course, you might be wondering, well, the data set are quantum states, so somewhere you need a quantum device. And indeed, in this setting, we are referring to what we call quantum enhanced classical simulation, where the idea is that you, of course, need to have access to the quantum memory where your ground states, say, are stored. But you can only access this for some polynomial time. You have like a shot budget. And you can only extract polynomially many features from that. And during this phase, what we're going to do is basically perform some classical shadow tomography technique, storing all the information we need to later reconstruct the expectation values of operators that we deem necessary to carry out the training. After that, you no longer have access to the quantum computer, and then we would deem quantum machine learning model as classically simulable, again, in a strong sense, if you want. If you can find a classical algorithm that, in polynomial time, so efficiently, can give you an estimation or a surrogate of your loss function L, this L hat here, in such a way that you can also train on this classical surrogate and find a classically trained optimal model, this h hat of theta star c, C is for classical, that achieves levels of classification accuracy that are on par with those of the fully quantumly trained model. Classification accuracy being just a metric of how good your model is performing on some previously unseen data, if you want. And of course, if you can complete all of these steps, if you want, then your quantum machine learning model has been actually dequantized in the sense of information processing, at least, meaning that there's never going to be the need of deploying it quantumly and train it by doing the infamous classical quantum feed training loop. All right, so what I'm trying to convince you in the next 10 minutes is that QCNNs fall exactly in this category, and all you have to do quantumly is just collect shadows, and then you're good to go on your laptop. All right, so as I said in the beginning, the idea is understanding what QCNNs look at and what the data sets actually are made of, if you want. And to do so, let me start from the first point. Let's denote phi dagger, the Heisenberg-Devolve measurement operator. Remember that O in a QCNN is a very small operator on a very few qubits at the end. And so phi dagger is just what you're actually measuring in the input, if you want. And then let me define buddiness and label it by K, the weight of whatever Pauli string, the buddiness being basically the number of qubits the Pauli acts non-trivially on, or n minus the number of identities. And then, and very importantly, let's assume that upon random initialization, what I'm doing is sampling parameters in such a way that each of the 2-qubit gates I showed you before is as if it was sampled from a local Q design over a unitary group. This is very important because it allows us to use Weingarten calculus, which is just some mathematical framework rooted in representation theory that allows one to carry out expectation values over this kind of randomizations. And we get from that this informal result where you basically, if you take the Heisenberg-Devolve operator of a QCNN, average over all the initialization and expand it in a Pauli basis, and then you pick whatever random Pauli, the coefficient in front of it is going to be exponentially small with respect to the buddiness of the Pauli. To better grasp this, let me quickly introduce this quantity, which basically, we call them K-purities, but basically, as you can see, it's just a squared norm or whatever operator O over the subspace of Paulis with fixed buddiness. So it's the total support of O, if you want, on Paulis with a given buddiness K. If you compute this thing for the average Heisenberg-Devolve operator of the QCNN, and then normalize it by the number of Paulis you have in each of these subspaces, you get this exponential decreasing behavior. And you can see from the very numbers that you have on the left that basically already at k equal 4, they become negligible. You can understand that on average, upon randomization, a QCNN is only actually supported on very small Paulis. And this, if you want, already smells like classical simulation, because it's basically screaming at us, just work here. I mean, just keep track of the coefficients of these polynomially many Paulis, because the size of these spaces is written there on the right. It's just polynomial as long as k is order 1. So in a way, this already informs us that we can classically simulate a QCNN at its randomization by just keeping track of the coefficients it's going to have on these small subspaces. So now we turn to the data sets and ask ourselves if the relevant information in order to carry out the classification task will be encoded exactly there. And spoiler, for all the data sets in the literature, the answer is yes. And in that case, we call these data sets locally easy, meaning that they can actually be classified just by measuring these Pauli observables with low k. And this will be all you need to actually tell the phases apart. What does this mean? Now, basically, so we know that on random initialization, we have that the QCNN lives in this small space, and these data sets can be classified in this small space as well. So we have the start and the end point of the training fixed. We still don't know if the training needs, for whatever reason, to leave this classically simulable space, but upon an extensive study of all the data sets in the literature, we were able to find that this is never the case, actually. So in all the successful training in the literature of QCNNs, this is what's actually happening. So the data sets are locally easy, and here is a schematic representation of our main results. But maybe this is an even better schematic representation. So at the end, the success of a QCNN only lies in the fact that it's been tested only on very easy problems. All right. So to conclude, let me show the simulation algorithm and some classification plots. So what we got so far is that QCNNs plus local easy datasets means that everything can be studied by looking only at small Pauli information. Again, by small, I mean low-bodied. So how do we actually do this simulation? How do we keep track of the coefficients there? We did so by resorting to Louisa, which is one algorithm in the family of Pauli propagation surrogates. Here, the idea being that whenever you need to estimate some expectation value, just like our predicted labels if you want, it's easy to show that at the end of the day, it's just the inner product between the coefficients of the states and of the Heisenberg-Devolved operator over, say, the Pauli basis, whatever basis would do, actually, but in this case, the Pauli basis. So d alpha are the expansion of rho in the Pauli basis, and c alpha of theta, those of the Heisenberg-Devolved operator. And now alpha would generally run from 1 to 4 to the n, of course, but the idea is that we'll just truncate those indices to the relevant polynomially large subspaces. And so now you can start to ask yourself how to cleverly do this. One thing is that you can, since you have access to the data set, you can invest some pre-computation time to understand from the data sets what indices, which operators in these subspaces are going to be the most important ones. As an example, say that you estimate the alpha via Pauli shadow techniques. By the way, we know that since we only want to estimate low-bodied Paulis, classical shadows are going to shine because the shadow norm is going to be small, so like you can get high accuracy there. But then you can also look at the observables that have the highest variance over the data sets, because likely those will be the ones actually carrying the transition, so carrying the information about changes from face to face. And then once you have all of this set up, so you know what kind of operators you want to look at, what Louisa does is you start from your measurement operator at the end, and then you start throwing gates at it. Now, assume that O is a Pauli and the gates are exponential of some other Paulis. It's easy to see how applying a gate splits it in other Paulis, and so creating this kind of paths in a sort of Pauli path integral approach. And then you basically just truncate these paths as soon as you deem them like either too bodied, too heavy, I don't know, like setting some threshold, here k equal 2, for example. But also you can use other clever ideas, such as at each time you apply a gate, you'll pick up some trigonometric function of the coefficient. So if there's too many of them, if the degree of this polynomial of trigonometric function is too high, this function is going to oscillate too fast, and you can drop it as well. All right. So this is how you basically compute classically the coefficient C alpha. Then you just multiply them by the D alpha that you get from the shadows, and you're good to go. So to conclude, a few classification plots, I guess. We studied these 4 models, again, by the techniques I just told you. Let me start through the first one more in detail, and then just breeze through the others. So here you're seeing the Heisenberg bond alternating XXX model on more than 1,000 qubits. It's just a standard XXX Heisenberg interaction, but now the coefficients are alternating from even to odd sides between these two values, J1 and J2. And depending on the ratio of these two coefficients, you get a phase transition between a trivial and a symmetry-protected phase. And the heat map I'm showing there is the test accuracy, so the accuracy on a test data set, as a function of the number of snapshots you take for each shadow evaluation, so basically the number of shots you do, and the number of training points. And you can see that already for, I don't know, like 50, 75 snapshots and 10 training points, you can achieve close to 1 accuracy. So, and also, like, you only need buddiness k equal 2. So probably this is the most important thing. This data set is, I wouldn't call it locally easy. It's rather locally trivial, because you just need very, very small operators to actually classify it. Then we also studied the Haldane chain, which was featured in the original QCNN paper. let me just point that in this case, the buddiness is 3, still very small, and that we can still achieve like 1 accuracy. Then we also studied multi-phase classification tasks such as the cluster Hamiltonian. Again, not much to say. We can achieve test accuracies that are higher than those previously achieved in the literature with our classical simulation algorithm. Here the buddiness is just 4. So I'll conclude. I hope I convinced you that QCNNs appear to be so successful because just because the data set they've been tested against are very easy for them. And also, since there's no currently evidence for QCNNs being able to solve hard problems, we should probably reconsider their place among like the upper echelon of great quantum machine learning models. However, enough with the shade to the QCNN. We didn't fully dequantize this model. Of course, problems might exist where you actually need to deploy everything quantumly, and that would be actually amazing. But maybe for the moment being, we should rather foster a quantum measurement enhanced classical machine learning approach where we find clever ways to extract information from a quantum data sets and then let our laptops do the job. Or also maybe think of it as like we can classically train everything and then afterwards maybe compress, find the optimal representation of the optimal parameters you found, and then deploy it quantumly. And while we can expect this kind of lessons that we learn from the QCNN to hold for whatever successful quantum machine learning model, probably the point here to be learned is that quantum machine learning as a community is in dire need of truly hard data sets to test their models against. And with that, I'll thank you for your attention, and any question is very welcome.
Okay, so a quick remark, first of all. The QCN architecture you cite from Lukin's group a couple of years ago is based on the Mira architecture, which is multi-scale entanglement, ansatz, etc. And previous results show that no matter where this is used, this is classically simulable.
Absolutely.
So we weren't very surprised when this paper came out. First of all, the QML community, that's a remark. Perhaps when you say non-trivial data sets, how those trivial, non-trivial data sets to benchmark learning models on could look like. What do you envision?
Yeah, so on the first point, of course, I mean, it's a logarithmically deep architecture, so you can always have like bond dimension that scales polynomially. Then there's a trade-off between classically computable, as in the sense of complexity theory, as it's scaling polynomially, and then the practicity of it, because after I believe like 100 qubits, any laptop would just die, or any supercomputer would just die. We can go like thousands with this method. So, but that's for that. As far as the hard data sets are concerned, we strongly believe topological data sets should be the ones we take on next, mostly based on this intuition that as long as the classifying features can be encoded in low buddiness operators, we'll be able to classically deal with that. While topological phases are defined by their global properties, and as long as you could actually encode some like by very large topological state, like some toric code, say, and so you have to compute this Wilson loop on like linear dimensions that are not trivial again, this would do the trick, we believe, because then you would have the buddiness of the actual order parameters scaling with the system size. So that's kind of the intuition, though the problem is then like actually coding up this stuff.
So actually, my question is basically following up on that point.
Okay.
I'm a little surprised that you're able to detect topological order with these low body operators. Is it because this is just SPT, or is it like do you think that
We
your
were,
protocol-
and I don't know, at no point I claim we were able to classify topological.
well, you demonstrated the simulation, right? Detecting
That's
that.
1D. Yeah, it's called topological phase, but it's 1D. So
I see. So
it's
you
kind
think
of a
that for
fake
true
topology.
like two-dimensional topological
yes,
order?
yeah, I was referring to 2D. Yeah,
I
there's
see.
not such a thing as topological phases. It's 1D
Yeah,
anyway.
yeah.
So.
Okay. I see.
Yeah. I was saying before, like a 2D topological phase, like a 2D toric code would do the trick, but we didn't do anything with that.
So are you saying that there's room for a possible like 2D QCNN that might circumvent your results?
Absolutely, yes.
Okay.
Yeah.
Hi, over here. Thanks so much for the interesting results. Okay, actually, there's a recent paper that was just presented at the other complexity track, talking about how you can simulate any noisy quantum circuit in polynomial time. And the key insight is essentially this thing that that noise will suppress the high Pauli weight paths exponentially. Are you aware of this and any connections with the work that you've done? Or the
I'm
ideas
aware of that. I don't think there's a straight connection. I mean, in terms of the simulation algorithm, totally. I mean, it's the same idea, just stay in those low body space. Our simulation were noiseless, if that can kind of answer your question. But yes, absolutely. I mean, as long as you can find a way to restrict you to a polynomial-sized subspace, you'll be able to find some classical algorithm to simulate.
See, thank you.
Hi. At the beginning of the talk, you mentioned that the convolutional neural networks could be useful for classical problems and also like specifically quantum problems. And so I wanted to ask you, what do you think of these results that you got for specifically quantum problems where the inputs and outputs could be quantum states?
Actually, off the top of my head, I don't know any problem where the outputs are quantum states. I don't know where QCNNs have
Okay,
been.
for example, like a quantum autoencoder.
Okay, I'm not aware of this kind of
Okay.
problem, so I'm sorry.
All right, thanks.
I think we should move on. So if you have a question, I guess you can ask.
Yeah, sure. I'll be
offline,
around.
But we should, for those who want to transition, you can move to the other room, and we'll resume at 4:30.